Bismillah ar-Rahman ar-Rahim. We are interested in this result. We have a sequence of random variables, xn, converging in distribution to the random variable x. We want to show that for a continuous bounded function g, expectation of g of x of n tends to the expectation of g of x as n tends to infinity. The sequence of random variables xn converges in distribution to x. This means that if we take the CDF of x of n at the point x, this is the probability that random variable xn is less than or equal to small x. This CDF converges to the CDF of random variable big X. That is, this probability converges to the probability that random variable big X is less than or equal to small x as n tends to infinity. We insist that this is true for every small x in the set of real numbers at which the CDF of random variable big X is continuous. If x is a point of discontinuity of the CDF, then we don't care. We want this limit statement to hold at small x, where the CDF of random variable big X is continuous. Function g from R to R is continuous and bounded. There is a positive real number m such that the magnitude of g of x is less than or equal to big M for every x in R. Big epsilon, that is a positive real number. Recall that for a CDF, we have two properties. The limit fx of x as a small x tends to minus infinity is equal to 0. Moreover, the limit of f of x of small x as x tends to plus infinity, this limit is 1. Because of this, we can obtain points A and B, such that the probability of random variable big X being less than or equal to A, so random variable X takes values here from minus infinity to A, we can make this probability arbitrarily small. We can choose A such that this probability is less than epsilon over 8m. M is this m here, the bound on the magnitude of the function g of x. Because we have this property here, we can also obtain a point B such that the probability of the random variable x being in the interval from B to infinity, this probability is less than epsilon over 8m. We need the points A and B to be points of continuity of the CDF, and I will comment on this later. So we need these inequalities to be satisfied, and also we need A and B to be points of continuity of the CDF of the random variable big X. To prove our result here, we need to show that the magnitude of expectation of g of xn minus the expectation of g of x, the magnitude of this difference can be made arbitrarily small. I can make this magnitude less than any arbitrary positive epsilon. So this is the idea. Let's insert in each expectation the sum of three indicators. So here we have expectation g of xn, indicator that xn is less than or equal to a, plus indicator that xn is strictly greater than a, but is less than or equal to b, plus indicator that xn is strictly greater than b. It is clear that the sum of these three indicators is equal to 1. Recall that the indicator is 1 or 0. It's 1 if the condition inside is satisfied, 0 otherwise. Xn is real. Hence, xn is either less than or equal to a, or is strictly greater than b, or is greater than a but less than or equal to b. For any given value of x of n, one of these indicators is 1 and the other two are equal to 0. We will do the same in this expectation. We will also introduce three indicators, but we will use big X rather than x of n. We can then apply the linearity of expectation and split this expectation here into three expectations. And we will do the same to this expectation after inserting the three indicators. We end up with 6 expectations. These guys here. Let's focus first on the magnitude of this expectation. By the triangle inequality, the magnitude is less than or equal to the expectation of the magnitude. So we have here magnitude of g of x, and the indicator is real valued and non-negative, so its magnitude is itself. Note that the function g is a bounded function. This term here, the magnitude of g of x, is less than or equal to big M. We can upper bound this by big M, take it outside the expectation. Then we have this is less than or equal to big M, the expectation of the indicator that random variable x is less than or equal to a. This expectation here is the probability that x is less than or equal to a. Because the expectation of a random variable that is either 0 or 1, this is the probability that x is less than or equal to a times 1, plus the probability that x is greater than a times 0. So this expectation here is simply the probability that the random variable big X is less than or equal to a. Note that a is chosen such that this probability is upper bounded by epsilon over 8m. So the upper bound on this magnitude is m times epsilon over 8m. That's epsilon over 8. But what about this first expectation? The random variable involved is x sub n and not x. Can we upper bound the magnitude of this expectation? The answer is yes. Note that because the sequence of random variables xn converges in distribution to the random variable x, then we have this statement here. Limit as n tends to infinity, the probability of xn less than or equal to a. This is the probability that x is less than or equal to a. This is true because we had chosen the point A to be a point of continuity of the CDF of random variable big X. Because this is true, we can find an n that is large enough such that the magnitude of the probability xn less than or equal to a minus the probability x less than or equal to a, that this magnitude is less than here any arbitrary positive quantity, let's call it delta. This is equivalent to the probability of xn less than or equal to a minus probability of x less than or equal to a is less than delta and greater than minus delta. So this probability can be upper bounded by delta plus this probability. To be more specific, since we have this statement here, there exists an n tilde such that for every n greater than or equal to n tilde, this probability is less than this probability, the probability that random variable big X is less than or equal to a, plus any arbitrary positive quantity, which we can choose to be epsilon over 8m. But the point A is chosen such that this probability is less than epsilon over 8m. So we have a bound on this probability, which is this guy plus this guy, that's epsilon over 4m. Also, the limit as n tends to infinity of the probability xn greater than b is equal to the probability that x is greater than b. Note that this is the complementary CDF and this is the complementary CDF. Moreover, the point B is a point of continuity of the CDF of random variable big X. We have this limit statement and it means something similar to above. There exists n bar such that for every small n greater than or equal to n bar, this probability is upper bounded by this probability plus any arbitrary positive quantity. Let's choose it to be epsilon over 8m, but this probability itself is upper bounded by epsilon over 8m. So an upper bound on this guy is epsilon over 4m. If we choose an n that is greater than the maximum of n tilde and n bar, then these two upper bounds will hold simultaneously. Now we can upper bound this magnitude here. By the triangle inequality, this is less than or equal to the expectation of the magnitude of g of xn times indicator that xn is less than or equal to a. This magnitude of g is less than or equal to m, which can be taken outside the expectation. We have the expectation of the indicator that xn is less than or equal to a. The expectation of the indicator is the probability that xn is less than or equal to a. Now we have this probability upper bounded by epsilon over 4m. M goes with m. Then this magnitude is upper bounded by epsilon over 4. And this one also will be upper bounded by epsilon over 4. What is our current situation? The difference between these two expectations can be written as 6 expectations. Now we have bounds on the magnitudes of 4 of them. 2 bounds are epsilon over 8. 2 bounds are epsilon over 4. The sum of these upper bounds is 3 epsilon over 4. In other words, the magnitude of interest is upper bounded by 3 over 4 epsilon, and epsilon can be any arbitrary positive real number, and then we need to upper bound the magnitude of this difference here. These are the two terms that we have not manipulated yet. We need to upper bound the magnitude of the expectation of this difference here. What we do is that we take the interval from a to b, and we have this strictly increasing sequence, t0, t1, t2. Basically, this is a partition of the interval from a to b. T0 is equal to a, t big K is equal to b. And then here we have t1, t2, t3, and so on. We need this partition to satisfy the following properties. Recall that the function g of x is continuous. Then g of x is uniformly continuous on the interval from a to b. If g of x is uniformly continuous, then for any positive number, here I will choose it to be epsilon over 16. There exists positive delta such that if the magnitude of alpha minus beta is strictly less than delta, g of alpha minus g of beta in magnitude is less than the positive number of interest. Here we take it to be epsilon over 16. We want our partition to satisfy that the distance between any two consecutive t's is strictly less than delta. So for every j, we want tj minus 1 to be less than delta. This means that if we apply function g to tj and we apply function g to tj minus 1, then the magnitude of the difference is less than epsilon over 16. There is something else that we need. which is that those t's are points of continuity of the CDF of random variable big X. That's the function big F sub X of small x. How can we do this? Conceptually, you start with T0, this is A, and then here is T0 plus delta. Delta again is determined on the basis of epsilon and of function G. Based on epsilon and function G, we will know the delta such that this property is satisfied. Starting from T0, which is A, we mark the point T0 plus delta, and we mark the point T0 plus delta over 2. T1 is chosen in this interval from T0 plus delta over 2 to T0 plus delta. Note that if we choose T1 to be in this interval, then the distance between T1 and T0 is indeed less than delta. And we are capable of choosing T1 such that it is a point of continuity of this CDF. Why is this? Note that the CDF may be discontinuous. However, a CDF is discontinuous at most a countably infinite number of points. The number of points in this interval is uncountably infinite. We are guaranteed that a T1 exists in this interval at which the CDF is continuous. Let's quickly review the proof of this statement that the discontinuities of a CDF, a cumulative distribution function, are at most countably infinite. Suppose that the CDF is discontinuous at the points x alpha, where alpha belongs to some index set. Discontinuity means that if we evaluate the CDF at x alpha, and if we take the limit as u tends to 0 plus, so u tends to 0 from the positive side, from the right, of f of x alpha minus u, then the difference between these two guys is strictly positive. That's a point of discontinuity in the CDF. We want to investigate the cardinality of the set big I. Let's call this site h of x alpha. The index set I can be written as a union, here we have n that is a positive integer, of the sets in. And what is in? In is this set containing elements x of alpha such that the gap, the jump in the CDF h of x alpha is greater than 1 over n, 1 over this positive integer n. The claim is that these sets are finite. Why? Recall that we have jumps in a CDF. The summation of those jumps must be less than or equal to 1. So this summation must be finite because the CDF goes from 0 to 1. If it contains jumps, then the jumps must sum to a number that is less than or equal to 1. If this set here is infinite in size, if it has infinitely many elements, then the summation of h of x alpha, where alpha is in this set, which is in, this summation is lower bounded by 1 over n by the definition of set in times the number of elements in the set in, its cardinality. If it's infinite, then this summation is lower bounded by infinity, and so it is infinite. But this sum is less than or equal to 1. Each in for every positive integer n must be finite. We have a rule which is that the countable union of finite sets or even countably infinite sets is itself countably infinite. The cardinality of the set at which a CDF is discontinuous is at most countably infinite. If we have an interval as such with uncountably infinite points, we are guaranteed to be able to find a point T1 such that at T1 the CDF is continuous. Now we have T0 and we have T1. What do? We repeat. We simply take the point T1 plus delta and T1 plus delta over 2. We choose T2 to be in this interval from T1 plus delta over 2 to T1 plus delta. If we choose a T2 in this interval, its distance from T1 is less than delta, which is what is needed so that this inequality is satisfied. And because there are uncountably infinite number of points in this interval, then we are guaranteed to be able to find T2 at which the CDF of random variable big X is continuous. We will continue to do so till we partition the interval from A to B. Let's rewrite each of those indicators in terms of the partition. So here g of xn, indicator xn between A and B is summation g from 1 to k, g of xn, and then we have indicators xn greater than tg minus 1, less than or equal to tg. And we will do the same to this indicator. The next step is to take this g of xn, write it as g of xn minus g of tj minus 1 plus g of tj minus 1. And here we take this g of x, subtract g of tj minus 1, and add g of tj minus 1. We take these two guys together and these two guys together, and we separate these two ones. So here we will get this sum, j from 1 to big K, g of tj minus 1, and then we have this indicator minus this indicator. Let's take the magnitude of the expectation of this difference here. By the triangle inequality, we can upper bound this magnitude as the sum of two magnitudes, the magnitude of this difference, and then the magnitude of this quantity here. The second magnitude is the magnitude of expectation, summation j from 1 to k, g of t j minus 1, and then we have the difference between the two indicators. If we apply expectation to the indicators, what is the expectation of this indicator? That's exactly the probability that this event is true. The probability that xn is strictly greater than tj minus 1 and less than or equal to tj. We can write down this probability in terms of the CDF of random variable xn. Specifically, this probability is fxn, the CDF of xn evaluated at tj. This gives the probability that xn is less than or equal to tj. And then we subtract the CDF of xn evaluated at tj minus 1. This is the probability that xn is less than or equal to tj minus 1. When we take the difference, we get this probability exactly. And we do the same after applying the expectation to the second indicator. We also get the probability, but with random variable x, and we can write it as the difference between the CDF of x evaluated at tj and tj minus 1. If we apply the triangle inequality to the magnitude of this sum, then this is upper bounded by the sum of the magnitudes. The magnitude of the function g, because it is a bounded function that is less than or equal to m, we can upper bound it by m and take m outside the summation. Inside the summation, we will have the magnitude of those terms. For this magnitude here, we can apply the triangle inequality for expectations. The magnitude of the expectation is less than or equal to the expectation of the magnitude. We can take the magnitude inside, and then we can apply the triangle inequality for sums, which is that the magnitude of the sum is less than or equal to the sum of magnitudes. We can then use the linearity of expectation and have this magnitude here upper bounded by this expectation and that expectation. Inside each sum, we have those magnitudes. Recall how our partition was constructed. Our function g is continuous, so it is uniformly continuous on the closed interval from a to b. And because of this, if we choose 2 points in this interval such that the difference between alpha and beta is less than delta, then the magnitude of g of alpha minus g of beta is less than any given positive number based on which we choose the delta, and our positive number is epsilon over 16. Note that here we have the difference between g evaluated at xn and g evaluated at tj minus 1. And look at the indicator. xn is living between tj minus 1 and tj. And tj minus tj minus 1 by design is less than delta. So here the function g is evaluated at 2 points, and these 2 points are separated by less than delta. So this magnitude here is upper bounded by epsilon over 16. And the same is here. So those guys can be upper bounded by epsilon over 16, which can be taken outside. When we apply the expectation, we get the probability. Now this summation here is a sum of probabilities that xn is between tj minus 1 and tj, and we are summing over j. The sum of these probabilities give us the probability that xn is between a and b. Okay, so this summation is probability that xn is greater than a but is less than or equal to b. And this is the probability that x is greater than a and less than or equal to b. Those probabilities can be upper bounded by unity. And so these two sums can be upper bounded by epsilon over 8. The last term to consider is this one here. We have m times this summation. Again, by the triangle inequality, this magnitude is less than or equal to the magnitude, and I take these two guys together, the CDF of xn evaluated at tj minus the CDF of x evaluated at tj, plus the magnitude of the difference of the CDF of xn evaluated at tj minus 1 minus the CDF of x evaluated at tj minus 1, like this. Recall that our very starting point is that we have a sequence of random variables xn. The sequence xn converges to the random variable x in distribution, which means that at the points of continuity of this CDF here, limit as n tends to infinity of fxn of small x, where this is a point of continuity of the CDF, this is exactly fx of small x. When we constructed our partition, we insisted that those points are points of continuity of the CDF. This means that this limit statement is valid for every tj. And what the limit means is that for n that is large enough, we can always find some positive integer, let's say big V, such that for every small n greater than or equal to big V, the difference between these two guys is less than some given positive quantity. Because we have convergence in distribution, and because the tj's are points of continuity of the CDF of random variable x, then each one of those magnitudes can be made arbitrarily small by choosing a small n that is large enough. By choosing small n that is large enough, I can make those magnitudes, all of them, at most epsilon over 16 km. We can upper bound each magnitude by this quantity. Now, if we multiply by the number of terms in the sum, that's k. If we multiply by m, this means that this is upper bounded by epsilon over 16. And this is upper bounded by epsilon over 16. That's another epsilon over 8. Given any positive epsilon of our choice, we are capable of making the magnitude of this difference between the expectation of g of x and the expectation of g of xn less than epsilon. What we need to do is to choose a small n to be large enough. Because we can do this for every epsilon greater than 0, then the limit of the expectation of g of xn as n tends to infinity is indeed the expectation of g of x.